Good afternoon, everyone. I would like to use the next 30 minutes or so to share some thoughts about how we could shape the future and what technology topics are that stand out. Basically, when talking about how to shape the future, it's also important to have a look at the world today. And in my view, the world today is both exciting and challenging. Like, digitalization is moving forward, and we have a lot of fascinating technologies going on. But on the other hand side, there are also challenges, right? Challenges that we face as a society and that we need to address. And during my little research for this presentation, I found 3 themes that resonated with that. So the first theme is uncertainty and change. Major events like the war and the pandemic, basically they have shown us that the world can change overnight, right? All to a sudden. Nothing is for granted anymore on that. And that's not only negative. We also have positive change, like the sudden, to most people I would say, the sudden appearance of ChatGPT, like end of the year, end of last year, or the boost of digitalization and corporate agility that came with the pandemic. So it's not all bad, it's also good change, but also good change is causing uncertainty. The next theme is scarcity. So as I see it, like everything tends to be scarce. Like people are scarce, cheap money is scarce, energy is scarce, resources is scarce, and so on. And this is triggering us to be more selective in what we do and also be more smart in how we do it. And the final theme is sustainability. As the negative impacts, especially of the climate change, get more and more visible and more severe. And I was just the other day, I was reading a report from the UK government that said that information and communication technology as a whole accounted for 4 to 6% of the global energy use in 2020. That's huge. That's really huge. And that has a high carbon footprint too. So as every data set, right, and every model and every system is consuming energy, we need to take care about that. So sustainability is a topic that should be on all of our agendas. Fortunately, digitalization and technology can help us, right? It's not only to deal with the challenges, but really to push us forward, right? There is so much going on. And I was trying to find and compile 4 topics that might be of interest. So the first topic is open people, open technology. And what I mean by that is, if you have a look around, like there is so much of open, it almost feels like a common philosophy. And I just picked a few examples here. And when looking into it, it gets obvious there is always a technology side of open, so the what you do, but there is also the people side of open, so how you do it, right? And to give a few examples, the first example is not really geospatial, but we all know it, like smart home, and how complicated it was, and how fragmented, right? And how confusing, right? So everybody has its own system, and we need to have like 10 bridges to get it all working, and it was still confusing. And what happened then is that bigger players opened up their system. So they introduced the works with paradigm, which was nice, right? It was taking us a step further, but it's still limiting. You couldn't just build the smart home that you wanted, right? It was limiting us as a whole. So, and then something significant happened next, which is that the competitors teamed up and created Meta in an open form. And for those who do not know, Meta is a comprehensive digital standard for devices, apps, and services. So in that sense, it builds a common foundation that vendors could use and build their own devices on top. And that allows them to really be sustainable in a way that they don't need to do all the plumbing, right, one by one, but they could focus on what they like to do and what they're good in. And it's also for us as a user, it's very efficient, because we don't need to have 10 bridges, we just need to have 1. So I think that's a very compelling example that shows the power of what can happen if you have open people and open technology. And a second example is the OGC, right? I mean, the Open Geospatial Consortium, and there especially the open APIs for the web. I think that's a very promising set of standards. It's lightweight, it's made for standard IT, web ready. There is no special spatial, so it's good to be integrated. And I think there is still a lot of potential into that, right? So it's, when comparing it to the Meta example, it's more like on the works with level. So we use that to open up our systems so other parties can participate. So there is a chance that we can do better. And what's needed for that? Well, I think, first of all, we would need the additional standards to cover all the both cases, the core cases. But then we may even need more than web APIs. And the last example for this open theme is Open Pioneer. And it's just to show things doesn't have to be big, right? They can be very small. So this is a brand new initiative that we have founded with our research partner, 52 North, and also with some clients to work on new technologies, right? On new things that we could use for spatial solutions. Yeah, and the first project being an open application framework, which is called Open Pioneer Trails. So if you're interested in that, please check it out or reach out to us. And the last point is there is also a whole set of technology patterns that you can use to build open solutions, right? So not so much the people, pure technology, what can be done there. Drivers, the drivers and the benefits, they match pretty well, and it is for sure collaboration, digital sovereignty, right? You can support this by technology and the adaptability theme. And cloud architecture patterns normally are very good in providing the flexibility needed to cope with the uncertainty, to allow to build up systems of components with standardized interfaces where you can mix and match, right? And there is one very famous architecture pattern which is called MAC, right? Microservice API first, cloud native, and headless UI. And if you're interested, I just added a short link to that, so you can read it up later on. But this is really a set of 4 principles that can be used to build those open solutions. The next theme would be data as a product. And data as a product is actually not a trend. It's not even new. It's like a couple of years in the market. But it's still there, and it has a value, and it's a core pillar of new concepts, such as data meshes or data experiences. And it's all about changing the perspective on data, right? And rather than gathering and managing more and more and more data, and to hope that value comes by magic, you take a different perspective in looking from the outside in. So what's the problem that you want to solve? And what data can you use? And what processes do you need for that? And which tooling? Right? And to really take all that and make a compelling product that users love, use, and will come back for more. And this is done by applying principles of product thinking and product management. It's pretty much the same as building a software product. A data product is not much different. And those are the problem-solution fit, right? They need to be easy to understand. They need to be easy to find. They need to be easy to use. They need to be trustworthy. You need to have a certain level of quality assurance. And they need to have a constant improvement loop, according to a roadmap, according to a vision, but also according to user feedback, right? And feature requests. And the example here, which I have chosen, is the Overture Maps Foundation. That's pretty new. They founded themselves by end of the year. And their mission, as I understand it, is to create and provide reliable, easy-to-use, and interoperable open map data. So, and when listening to the guys behind the Overture project and reading their document, right, it reminded me of Meta, the Meta example for smart home. there are so many similar things between both. So, I mean, those are the companies that are part of the foundation. And when these companies bring together their data, which they have, their tooling, their funding, their technologies, their expertise, you can imagine what the potential could be of that. So they could actually really build the foundational data products for the next generation of spatial information systems. I'm saying could because this is young. They just had the first alpha release in July, and they still have a way to go there. But there is the potential for this initiative to be the meta for geospatial data. So yeah, this is what they actually have. So buildings with the highest information to support 3D. They have transport network with road segmentations, 60 million places, and the administrative units. Everything is globally done. Yeah, and that's very basic, right? But it's a foundation. It shouldn't be more. These are the four main problems or challenges that they want to address. So basically, it's fuse data together from different sources, quality assure them, process them according to a target schema, and then just serve them, right? And the highlight for me is the global entity reference system. By what they mean is that they apply a global unique identifier to every object in their data. And that identifier is a very simple but powerful mean to connect business data, to connect your data, right? Or to connect different data sets that are sharing the same identifier. And that makes it really possible to build a huge ecosystem of compatible data products. And there is a promise to build a common, shared, and open map for us all, right? This is the foundation is run under the Linux Foundation. It's an individual company, and the data has been licensed with open data license as well. So we could just all use them, right? And it's early days, again, but the potential is there. All right, the third team is the blending of physical and digital. And this was, in the beginning, I was like, okay, we need to talk about digital twins to some extent. And then I found out, well, wait a minute, this is like a little bit broader. And I came up with this diagram. So what this says basically is that the digital twin, from my point of view, is more the current state of a constant development to blend physical and digital world. So we started with information systems, and we still have a ton of information systems out there, and that's good, right? And then maybe the next step is the Internet of Things, like making the map more recent, having the sensors inside. And then the next step could be the digital twin, or is the digital twin, right? We have more connected data, and we have data and behavior representing the physical twin. So it's a step in advance. And we have the prediction capabilities, we have the analytics, and many more. And the next step could be to link those twins for an ecosystem of twins, like the internet of linked twins. That could be the next step, right? Where one twin could fuse the other, and they work together seamlessly. So I can implement more use cases with that. And then we might end up in the metaverse or whatever that is, right? That might be the step after that. And the development has like two axes. The why is from data to knowledge. So the further we go, the better we can get knowledge from the data. So the data is easier to understand. We have the right analytics tools. And we can easily gain knowledge there. And the development on the x-axis is more like the experience that we have when operating with digital maps and digital geospatial data. And that goes all the way from I look on the map, right? I look into the map, being the digital twin, right? I can turn it and look into it. And the last step might be I'm an active part of the map. when we are in the metaverse. But the ultimate goal, actually, of this development is to make better and faster decisions, right? And to take better actions. And this is a powerful tool to actually address all of the three themes: the uncertainty, the scarcity, and the sustainability theme. All right, here's an example. This is using FME finally, right, on slide 19. Sorry for that. This is actually opening up public transport data from the city of Münster and push it out via an open API interface so it can easily be integrated and used in different scenarios. So this is a map of public transport. And normally those dots should be moving across the lines, right? They are not moving here, but they are, in fact. If you look it up, the link is under the screenshot. So this is basically on the IoT level, an information system with real-time data on top. And we could use the real-time data for different other scenarios, like digital signage, right? It's using the same information in a different style for different purpose, but it's both aspects of the same thing. So if we now go back to this development line, we could easily think, so what happens if we would like to go one step further and add the 3D? And they don't have it, but I found an example of Hong Kong. It's not really Münster, but yeah, I mean, you get the story. And they have a digital twin for their transport network, right? And the information and data is the same that we had in the 2D examples. So what would it take to make it more immersive, just to have the 3D data there and to have an app set up and some services and done, right? I think that's an easy win. The other example is currently in development, as you might see from the screen, right? It's a digital twin for emergency response for the federal state of North Rhine-Westphalia that we build right now. It's in development. And the current scope is really to get all the data in. So they decided to reuse spatial data infrastructure data sources also for the digital twin, which I think is good because we need to connect them anyways. But there are specific challenges, so I would say, to really blend them together and to build the corpus of the digital twin, and this is what we are doing right now. And when it's done, we will also add thematic data and thematic data sets for two themes initially, one being flooding and the other being wildfire. Right? And I have a flooding example that shows the value of 3D and the immersive view, right, if you have that. So this is a model of a flooding area where you can manually set the water level. And you can see what will happen. And you can see which roads are still accessible and which not, like for the early responders, right? So what can you do? And this is just displaying and visual exploration, but the step to automate that, right, and have a routing that can actually see the area and find a route across that, I mean, that's just a step away. All right, yeah, just a little bit more. Well, as we use the open specifications, the open APIs as well, this bus data, that's hard to see actually. The buses, right, they look pretty ugly. But this is the same data as the public transportation system, which I showed earlier. So you can mesh those data sets. And in this case, it's just a prototype, but they are looking forward to, let's say, integrate emergency vehicles into the map as well for a later state, potentially. Okay, so this is in development. There is an event by the end of September where at least the German-speaking audience might be interested in. They will give some further information on that. And the fourth and last topic, of course, is artificial intelligence. But again, just a few examples on how this could be used, very practical examples on how this could be used to address the scarcity and also the sustainability theme. So the topic made a huge jump, right? It's really like a jump. It's a black swan event. All to a sudden, bang, it was usable. And And we see, like, especially the generative models, as you guys do in your tools, we actually see this as the most and directly usable tool to handle with the scarcity theme. But also the predictive models and things like natural language processing can help to further enrich the digital twin and beyond. And 3 examples that I have. The first example is actually from ESRI. That's a model that is taking LiDAR cloud data, and it's processing every point in that point cloud and trying to give it a label. And those labels will then be set together like an object, and you can use it to find object in that cloud data, as you can see here. And this data can be extracted, you can make a mesh out of it, you can do all kinds of things. So it's adding some logic to it and some semantics. The other example is cows. Now that's a tool called Get3D from NVIDIA, and this is pretty interesting. It's not, I think it's pretty interesting. It's not geospatial, right? But what it does, it takes 2D images and it generates a 3D model out of it, right? I mean, for those of you who know how much effort it is to build a good 3D model, it takes days, it takes weeks. Right? And with this model, you can actually bring the time down to a few minutes. And this one is pretty good to actually make your digital twin more lively, right? To make it more immersive, make the experience better, but it can also be used to democratize the participation in digital twins. So if you want to join in like a city planning and there is a proposal, rather than just saying, I can use this or that, you might actually use to upload an image and say, well, I would prefer this building there, right? So it's a totally different level that people can participate. And the last example is SAM, Segment Anything from Meta. It's also pretty new, beginning of the year. And what it does, it takes imagery and it segments and it takes objects out of the image, right? And segmentation is not new. I mean, we've been doing this for years. But what is new here is the model works without training. So you don't need to train the model to understand the concept of what a car is, or what a building is, or what a tree is. The model understands the concept of an object. So you can just feed it in imagery, and off you go. And this is an image which I put into the model, and I choose the prompt, pick every object that you can get, and it's then picking raster and then finding all the objects which are in that image. And that's out of the box, right? So you can easily think of a pipeline where you have like a JSON writer that takes those objects out, georeferences them, and does something with it, right? And it's groundbreaking. I really think it's groundbreaking because it's directly usable. It's promptable and it can be integrated for land classification, counting stuff on a map, counting cars or endangered species, whatnot. It also works with a little bit more complicated imagery, of course, so this is pretty amazing. And what it also does is it works on video streaming. So you can feed it in a real-time video stream from your headset, like spatial engineering is the term from Apple, and it will find objects in the video stream on the fly. That's not a video from me, right? I copied it from the website, but it's amazing, right? It's not object recognitions. You don't get a bounding box around the object. You get the object itself, and you can pick it up, you can change it, you can do something with it. And I think that's a good step towards the metaverse and to a more immersive experience. So SAM is available under the Apache 2 license, so everybody can use it. Yeah, and it can be fine-tuned, right? If it doesn't do the job as you like it, you can fine-tune it to better find cars, to better find whatnot. And of course, I think we will have a SAM transformer in the future, right? Maybe tonight, during the hackathon. All right, that's it for the examples. To sum it up, So uncertainty, scarcity, and climate change, that will keep us busy for a while. I mean, it is what it is, right? We need to deal with that. Digitalization and technology innovations can provide us with essential and exciting tools. They are at our hands, right? They are here today. And to me, it's important. It's not only about the what, but it's also, and maybe even more, about the how we do things. And for that, collaboration and openness is key for success. All right, so that was it for my talk. Thanks for listening. I hope it was interesting, and well, thank you.
I would like to introduce the next speaker, Peter Veenstra from Pivot from the US, and he's going to talk about how FME is helping in the ever-growing need for green energy.
Good morning, thank you. The topic of my presentation is bring life to data to make better decisions. From data to location intelligence for renewable siting and routing. Pivot is a small location intelligence company. We offer our services as a software as a service. We've been around for about 4 years, 27 people, all of us working remotely. A few years back, we were purchased by a geotechnical engineering firm, Terra. They specialize in geotechnical engineering, environmental facilities, and materials. They have 5,000 people and 175 offices, some of them remote. I've been doing the GIS thing for 32 years. I had to count on all of my fingers to figure out how many years I had been using FME, and that was 22. So first, before I start, I'm going to start with a thank you to Brett Holmyard from Safe Software. He challenged me on this presentation. He said, I saw your presentation at the last conference on metadata, but is there a way for you to show all of that data that you create and bring it to life? Also, I'd like to say thanks to Dean Hintz from Safe Software as well, because I saw his climate resiliency presentation, and that got me thinking about different ways that we could bring our data to life, and I'll explore some of that. And of course, Emily, Don, Dale, Safe, and Encore for allowing me to present today. It's a real honor. So when you try to bring life to the data, take it from being dark and not understood to allowing your clients to make better decisions, those decisions for them lead to results. And the results come from the information that we provide to our clients. And that information is really just created from the data that we go out and curate from all the different data sources that we have. So I guess the dissertation of the presentation, the thesis is, FME brings life to our data, our platform, and our data brings the users to helping make them make better decisions. So in the pipelines and electric transmission routing, siting, renewable sphere, people need to make decisions incredibly fast. Land is at a premium. The presentation that wound up the conversation yesterday about scarcity, land is very, very highly competitive to get. So getting to it quickly and understanding the site local intelligence about a particular location is paramount. If you read anything about the news, and we stay involved with that from a United States perspective, there's a lot of polarized public opinion and political opinion around whether or not solar farms and wind farms and electric transmission lines are viable and need to happen. And so the idea of being able to acquire land and understanding all of the things that influence a potential purchasing decision for that land is super important. As I drove along the Autobahn and managed to sneak a peek out every so often, I saw lots of wind farms, lots of solar farms, and lots of electric transmission. The United States has those things as well, but you can just imagine by looking at anything within the news that there are very strong views about whether or not that should happen. So for us, location intelligence just requires data. The hex images on the right-hand side show that our data has been 8 years in the making. We have 123 spatial data layers. We just crested 500 million records. We store it all in PostGIS. It allows us to store multiple geometries hosted on Amazon. We have 180 data agencies that we pull the data from, 4,000 data sources. We use FME Flow to ingest, curate, and QA/QC all of our data. And as a result of this, in my presentation at the last UC, we have row-level metadata. We can look at any record in our database and understand exactly where that data came from. And every 30 days, we're checking to make sure that we have the latest available data. Part of our process is to classify all of that data into larger groups and then again into subtypes. So 123 tables gets broken down into roughly 8 categories: boundaries, geotechnical, hydrology, land use, property ownership, energy, infrastructure, jurisdiction, community, society, ecology, and weather. And if you want to see the data layers that we have, and it is for the United States only, but it's available on our website right there. So the data needs to be right. We have to understand why our end user wants to use the data. Then we use QGIS to do our sourcing and our research to say, yes, we think this is a valid data source. FME Form is used to curate that data into a standard format that our applications on our platform can read it. We aggregate that data, we perform QA/QC on it. As I said, it goes into PostGIS, and then we publish it with FME Flow hosted. Get used to that. Again, all on Amazon. And then it's consumed through our web map with GeoServer and the Google Maps API. So this is a lot of workbenches for that much data. The last we looked and ran a count on our FME Flow hosted site, we had 36 repositories and about 850 plus workbenches. I think later on in the presentation I say 839, but that is changing as we find new data sources all the time. So one of the powers of FME that I think is really cool, and we all probably as FME practitioners take advantage of, is just the ability to document how you take source data and transform it into the data that you want. And there's tons of tools out there, but just the basic FME building blocks and transformers, like the attribute manager, the test filter. We live and die by these things. And what's really nice about it for me, not being as technical as the rest of my team, I can go look and see any FME workbench, pull it down, take a look at it, and if it's not documented with annotation, I can open up the attribute manager and get a really good idea of what transformation are happening. And run something locally just to make sure that the data is going the way it needs to be. This top workbench picture breaks the rule of less than 10 transformers in a workbench. But this is our massive data QA/QC load that goes into our bronze level database. And that first thing we do is make sure that these data all have metadata assigned to them. Have we curated the metadata? Do we have the metadata for this data load in our existing database? The next thing we do is make sure that we classify our data sets. We have 123 layers that are in 8 main categories, but that gets broken down to about 5,000 subtypes. And we're adding new subtypes, or sometimes we have to classify and group data into the subtypes. So it's really important to make sure that all those subtypes are present, because the application logic for choosing siting comes from those subsite classifications. Another thing that we use FME for is the idea of smart parcels, and I'll show you some examples of what I mean by a smart parcel. Smart parcel is the marketing term. It's really a composite parcel. I'm sure you're all used to tax map parcels where individual parcels are owned by a different person, and they have a mailing address for the owner, and they also have a mailing address where mail gets delivered to them. This aggregation of smart parcels goes beyond just aggregating parcels that have a common owner name, but also what is their proximity to a substation or a large electric transmission line? What is the percent slope and different categories? And all of that is done with FME, storing it in JSON as attributes so that our application can consume it. Excuse me. The other big use for us is taking all of the readily available DEM data that the United States Geological Survey provides and the land cover data and tiling those into the PostGIS database in raster format. And this allows us to save a bunch of space rather than having large DEMs in file format that we have to read on the fly. They're now in PostGIS, and all of that work is done with FME. So, that was my obligatory 5 slides on FME workbenches that nobody ever gets when you show them at a presentation because you have to dive into the weeds. But that's just to show we use it all the time. Yesterday in the presentation, you heard people saying, I don't know how I would survive without FME. We're in the same boat. FME drives our total data engine. Our application is what brings the data to life. So if you forgive me, I will dive into a little bit of that just to show you how the data are used. The first thing that we discovered, and again, Dean Hintz put me onto this one, was the H3, the Uber H3 hexagon spatial index. This is New Orleans, shown in OpenStreetMap. And this is a storm surge raster. And raster data is great because it provides a visualization and you have data at the different pixel levels. But the problem with raster data is that for our system, if you click on the map to get information, we don't pull it out of a raster, right? Because you'd have to have a feature service running there. And for that many records, that just gets crazy. So we're going to look at aggregating the raster into these H3 hexes and present those. So above the first image is the raster, the second image is the 10-level hex, this is the 7-level hex, and this is added to the 4th-level hex. And you can see for the entire United States at level 4, there's 7,705 hexes, but at level 7, 2.6 million, and at level 10, 906 million, if I have my math right. And we had somebody say, we need to go one further. And that puts us into the 2.9 billion. So if you go back to a couple of slides, we currently have 500 million records. That would immediately quadruple the size of our database. So we're still fascinated by this. If you have an Amazon representative and you use Amazon, please advocate for them to add the H3 extension to their RDS post-GIS implementation, which they currently don't do. So we have to use FME to do it. But getting into, we do a lot of that work in post-GIS, and it would be really great to do it natively there. But again, just to show you an example, here's a 4-level hex. Here's that same data at 7. Here's that same data zoomed into the black box at 10. And then here's that same data zoomed in with the raster on top. And the fidelity is actually pretty good. Now, some people will say, I need to know the exact cell. But when you're dealing with the scale of the United States, and what we're trying to do is prospect for solar sites, not give them the engineering level work. That comes later. But they need to rapidly go through and look at the data and the sites as fast as they can. And we see this as being super, super useful, not only for showing raster data in a vector format in our platform, but where do we have data and don't we have data? When was the data less developed and last updated? Cultural and historical resources, archaeological sites need to be preserved, and you have to be a licensed archaeologist to access that data, but we're allowed to show heat maps, and we see this being a really, really powerful way of doing that. And with 110 different data layers, we could pull attributes and put them into this spatial index, which resides in a database, and that is a perfect segue for us to start using this to use artificial intelligence on the data, not only just for correlation and trend analysis, but where are there patterns that we didn't know? So for us as a platform, going to our clients saying, hey, here is a site you worked on. Would you like to see 50 other sites in the same state that are comparable? This is a huge thing for allowing people to quickly find the properties they need and vet them earlier. This is our routing example. Again, bringing the data to life, you'll see the sort of end result. The first thing we do is we allow our clients who want to route a pipeline or electric transmission line from point A to point B to create what's known as a play. Play is preferred, low avoidance, and exclusion. So they can take all of our data layers, as you see in this right here for landslide risk. They could choose the subtypes and apply whether or not they want to exclude it from routing analysis. So we had a client give us a 10-mile line, 16 kilometers, and said, this is our route. This is what we think to do. So can you imagine them looking at 123 different data layers? So we do the work for them and give them a suitability surface. So you can immediately see that their red line route starts to go through some gray exclusion areas on our system. And you can see that the blue is sort of the optimal path. And then we actually show them, this is the cost surface. And you notice that that red line route goes through some orange areas, which happen to be schools with a large buffer saying, don't go through this. You don't want to put a pipeline near this. But our system routes the little yellow pipeline to the north, so we're able to allow them to take all of this data very, very quickly that we produce with FME into our system and generate reports that tell them what is the cost for routing either an electric transmission line, a carbon sequestration pipeline, or an oil and gas pipeline. Going back to that composite parcel example that we use for FME, if you look at the top and the bottom, these graphics, and along the bottom you'll see a chart. And this is, show me all the number of parcels that are greater than 200 acres. Solar farms, wind farms take up a lot of acreage. And you can see the difference between the composite parcels at 200, 300, 400, 500, 600, 700, and 800. Now, admittedly, a lot of these are parks, but still the density of available parcels as a result of us doing this composite parcel analysis is very, very powerful for us to determine sites. Quickly looking at the state of Iowa, 142, I think the cutoff was 500 acres versus 2231 in terms of the number of composite parcels we could do. And then if you look at these composite parcels, you can start to do analysis on top of it. Show me the percentage of land cover. Show me the usable farmland. Break it down and find out who is the owner and create the reports on that. Again, our system does that work, but all of this data is pretty much delivered to them with FME. And what's really, really cool about this is this on the left are all of the composite parcels greater than 500 acres. On the right, you can see how they're broken down into the individual tax parcels. But by doing a little bit of spatial analysis, we can find out beneath that the owner of a smart parcel to the north owns a bunch of parcels to the south that actually turned out to be a better candidate. So if you use our application and you can see the screens, you can see the presentations of the data layers in the left image on the right, and you can see all of the requirements about usable area. And this one smart parcel becomes incredibly, has a lot of potential for a solar site because the colored areas there are the areas that can't be used for a solar farm. The rest of it can, so it has a high potential for solar siting. So the visions of success for our platform, for our clients, is to allow them to go from idea and area to finding candidate parcels for solar farms and wind farms, or the most suitable path from A to B, which are not really complicated GIS processes in themselves, but they rely on data. And it allows the clients to make data-driven decisions. So they can say, I'm going to invest the time and start doing the detailed engineering analysis of these sites very, very quickly. And it helps them just remove uncertainty. When we present this to people, it's all about the software. But what makes that tick is the data. And what makes that tick is FME. So thank you very much for your attention, and again, for the opportunity to present. And I think I did it with 3 minutes to spare. So.